Okay. Thank you very much to the organizers for the invitation to speak today. I have a couple things to say just before we get stuck in. First of all, I'm speaking actually on behalf of my colleagues, AJ Jane and Anne Cleves. AJ was due to give the talk today, but unfortunately he had a very urgent family matter, so asked me to step into his rather large shoes. So all credit to the great work here really goes to AJ and Anne and their collaborators. The second thing is I'm going to be talking about something a little bit different. So I'm actually going to be talking about building machine learning models based on physical principles. And you may ask, why am I here at a free energy conference talking about that? Is because what I will show you is how this approach can be very synergistic with the simulation-based methods we've been hearing about so far today. So I'll start by giving an introduction to the motivation and a high-level overview of a method called QuanSA, which stands for the Quantitative Surface Field Analysis Method. Then I'll talk about some benchmarking work done in collaboration with Steve Johnson at BMS, and really illustrating the synergies of this method with free energy methods, particularly FEP+. And I'll close by giving just a quick snapshot of a case study of how this can be applied prospectively in the context of a project, and actually rather conveniently talking about macrocycle natural product project, sort of leading on nicely from the discussion that we've just had before drawing a few conclusions. Okay, so first of all, to introduce QuanSA and its motivations. So first of all, predicting affinity with conventional machine learning methods is really challenging. Why is that? Well, because when we're building an affinity model, we really want to train based on the data we have now and the compounds we have now and make predictions for new compounds in the future. And when we're thinking about models based on sort of simple structural features, that breaks one of the sort of fundamental assumptions of machine learning, which is that the population on which we're training the model is representative of the population on which we want to make predictions. So unless we have a very large amount of data, which is very rare in the context of an ongoing project, not maybe hundreds or even thousands, but maybe tens of thousands or hundreds of thousands of compounds to build such a model, we're not going to get good quality predictions when we want to make predictions for our new compounds. So to overcome this, we need to really be building models based on the fundamental sort of physics and chemistry that drive the affinity of the compounds that we're looking at, something that will be very familiar to those in the room. Now, if we want to do this, of course, sort of simple sort of 2D representations are probably not going to be sufficient. This isn't working, okay. We really need to be thinking about 3D representations of our molecules. And of course, this isn't a new concept. And if you go back almost 40 years to COMFA, of course, this was the underlying principle. We need to be thinking about those 3D structure activity relationships. But even there, we have to be careful not to be led astray by the assumptions that we're making. So here's a very nice example. If we look at dihydrotestosterone and estradiol, if you look naively at the structures, you might imagine they're just going to overlay in the sort of obvious way there. But if you look at the actual bound structures of these, estradiol is flipped both sort of left to right and top to bottom in its bound conformation. So if we didn't understand that, we might be making incorrect assumptions in making the predictions of their common affinity. So how does QuanSA address this? Well, first of all, in terms of the representation of the molecules. Of course, when we're thinking about how a protein interacts with our compounds, it doesn't really care where the atoms sit. What the protein sees, of course, is the surface that interacts with the binding pocket. And so the eSIM and QuanSA approaches use the same sort of fundamental representation, which is essentially by looking at molecules in terms of their surface by using a set of observer points that surround that molecule. And they sort of mimic what the protein is actually seeing about those molecules. And we capture not only the shape, but also the hydrogen bond donors and acceptors, and also the Coulombic effects at those different observer points here. And you see this actually nicely explains that sort of common activity between the two sort of flipped conformations of DHT and estradiol here. In fact, although there's very little sort of overlap in terms of the atomic positions, there's a very strong congruence between the molecular surfaces, the interactions that those different molecules form. So QuanSA uses this representation to induce a model to predict and explain that binding affinity. So it starts with a training set of compounds. It generates an optimal alignment of those, a mutual alignment between those. Now, the second very important addition here is that each molecule is not represented only by a single conformation, but actually there are variant poses for each individual molecule. This uses a concept of multiple instance machine learning, where each molecule is represented by multiple poses within the overall induction of the model. Having got this sort of collection of poses for each individual compound, we can then represent those in terms of the observer points and the properties. And the model itself is based on actually 6 parameters at each observer point that captures the optimal distance, the direction and distance to hydrogen bond donors and acceptors, and in energetic terms, in terms of the Coulombic effect of local charges as well. And based on this, it induces what we describe as a pocket field, sort of illustrated here, the sort of overall shape and these various interactions represented at the different observer points. Now, just to take a step back, what we do to actually build the model is take a set of compounds with an known affinity. That's just blanked out for some reason. There we go. With known affinity, we don't actually require any structural information. If you do have information based on crystal structures, you can, of course, use that. But at basic, you just need a set of smiles and activities. This can represent quite a wide diversity of different compounds. It generates that alignment. Within that, of course, as I mentioned, each compound is represented by multiple poses, which are used to define this pocket field. This QuanSA pocket field is then iteratively refined along with the poses of each individual pose of each individual ligand. There's sort of an adversarial game where they're both being mutually optimized against one another to best explain the differences in activity between those compounds. So it's important to use both active and inactive compounds to understand which of the features at which of the observer points are most explanatory of the difference between the affinities of those compounds. In that optimization, the strain of each individual pose is also taken into account. And once that sort of optimal pocket field has been defined, we can take a new compound and we can actually make a prediction of its affinity based on the various interactions with those different observer points. Now, you don't just get a number, though. It's not a black box. You actually get a lot of information to support that prediction. So as well as the score or affinity, you actually can see a pose that is predicted for that compound as well. And also prediction quality metrics provided to understand how different is it from those compounds of the training set, if it's likely to violate any exclusions of that pocket field as well. So exploring sort of new areas that weren't represented by the training set of those compounds. And we can make predictions for really quite diverse sets of compounds with different scaffolds. So here you can see a few examples of predictions. And here's the actual molecule being predicted, its pose, and that is the nearest neighbor in the training set. So you can see where you've got the sort of an obvious correspondence between them. Of course, it generates an alignment that won't surprise anyone, as well as a very good prediction of the PKI. But even when we're moving into new scaffolds, we can still get very good predictions, and we can see why and explain why that prediction has been made and what that alignment is. And then as we extrapolate further, we get to really quite different scaffolds here, which are likely to be quite different from the compounds in the training set, but indeed are still, maybe not quite as accurate, but are still making good predictions for this really quite diverse chemistry. And actually building and applying these models are very tractable. So it takes just a few hours to build the model. You can inform this with protein structure where that's available, but it can be applied, in fact, based on data that has no sort of target known, for example, phenotypic data. When we're making predictions for a new compound, it just takes a handful of seconds to run. So it really does enable quite large-scale applications. So let's look at a comparison between QuanSA and FEP+. So this is some work done by AJ and Anne with Steve Johnson at BMS. So first of all, looking at one example project, the LFA1 project at BMS, which is sort of a mid to late stage lead optimization project with really quite substantial structure activity data. So this was based on a timestamp data set where the chronological order of the compounds is well known, and so used a temporal segregation into training and holdout sets used to build and refine the model, and then a future set of compounds to make a prediction. So here in the top right, you can see some illustrative examples of the compounds in the training set. So from quite different scaffolds as well. And here's an alignment between those three generated as part of the modeling process. We can make predictions for new compounds. Again, you get the pose. You can understand the different points of interaction there. And you can sort of compare that, in this case, with the actually measured activity. And here on the right-hand side, we're showing a scatter plot of the experimental PKI against the predicted PKI. So when making predictions on 67 future molecules, it had a mean unsigned error of about half a PKI unit and a very statistically significant rank ordering by Kendall's tau. Now, when we look at FEP+, it could only be applied to 17 of those future molecules because some of them were moving beyond the domain of applicability. But where it could be applied, what you can see is really very similar levels of accuracy in terms of the mean unsigned error between QuanSA and FEP+. But what was really notable, actually, is when you took a hybrid, just the average of the individual predictions for each compound, it generated a lower mean unsigned error. So there seemed to be some complementarity between the two different methods. So obviously this is based just on a single observation. So they then went on to look at, well, does that generalize across multiple targets and multiple data sets? And so this was applied to the Schindler and Abel sets, so a total of 16 different targets. And this view you can see for the Schindler data set, if we look at one example, the SHP2, we can actually look at follow this through in more detail. Now, obviously, when you're looking at the FEP predictions, it's based on a single reference compound. We need to give QuanSA more information in which to build a model. So to be rigorously fair, we can only use data or information prior to the publication date of those compounds, so that we're using historical information to inform that prediction. So known PDB structures prior to the reference date above, and also ligands with activity published in Chembl, again, prior to that date were used. Now, of course, you can find many compounds with activity data published in Chembl. So these were filtered down to those that were at least similar to the reference compound using the eSIM 3D similarity method. And the final focus training set is shown here in terms of its alignment that was used to actually build the model. And there were only 15 compounds used to actually build this model for SHP2. So if you look at them here on the top, you can see some representative examples of the training set. Most of these were shown here are actually from the same patent as the FEP reference, but it does include other more diverse scaffolds, including, for example, this thiazole here in the top right-hand corner. So a greater diversity in terms of the scaffolds and even the charges of those compounds. And if we look at the prediction set here at the bottom here, again, what you can see is good quality of predictions. And again, that sort of hybrid, taking the average between the FEP and the QuanSA prediction, tends to give a lower error relative to the experimental value. You can also see the alignments here at the bottom here. And another interesting thing to note here is that actually there's sort of different positions of this A-mean on the right-hand side here. And you can see by the different sort of sticks here that represent the strength of those interactions that you're sort of capturing an OR. It's actually accepting two different orientations as contributing to the affinity of those compounds. So when we actually expand that and look at all of the 8 targets in the Abel set here, you can see, again, the scatter plot of experimental versus predict on the left-hand side, a cumulative histogram of the unsigned prediction error, here, and then a distribution of the sign prediction error. And again, what you're seeing is that combination consistently is giving, on average, a more accurate prediction. So the shoulders here, the largest and most egregious errors, either by QuanSA or FEP+, or to some extent being corrected by the other method. The errors for these two methods are uncorrelated, and so we can sort of take the average to improve upon that. And again, very, very similar picture for the Schindler set as well. Again, for 8 targets shown here. And again, you're seeing this distribution where we take the hybrid being sharply peaked in the middle, and the shoulders are sort of being removed, or either method is producing the largest errors. Now, we can also think about applying this method to a much larger scale sets of compounds. So following from this, the other data from Kemble, again, after the date of publication of the data used to build the model, were used as a sort of a screening set. Now, we can do this across quite large sets because the average time per new molecule is about 10 seconds to make a prediction. That includes all of the sort of 2D to 3D conformational search, fitting and scoring in the pocket field. And this is on sort of very standard hardware. It doesn't even require a GPU to achieve that performance. And on the right-hand side, I'm showing some examples of predicted active compounds from those collections of compounds. And what you can see is really quite different compounds from either the reference compounds. So here I'm showing the predicted compound. This is the FEP reference in each case, and the nearest neighbor in the training set. And we can see it's making predictions for really quite structurally novel active compounds, including here on the right-hand side, a macrocycle, which is actually being correctly predicted based on non-macrocyclic compounds here. In addition, this was also tested with 1,000 decoys to make sure it's not just over-predicting activity, and the specificity was also very, very high, typically less than 1 in 1,000. Those 1,000 decoys was predicted to be active for each of the targets. I think the maximum was about 10. So what we can see from this is that QuanSA and FEP are essentially equivalent in accuracy, but also synergistic. And we can sort of understand this because one is providing a very sort of protein-centered view, the other sort of ligand-centered view. And so these different perspectives are leading to uncorrelated errors that cancel when we start to take the averages here. We can apply QuanSA to screen large-scale sets of compounds with both high sensitivity and supposed to be specificity as well, excuse the typo. So we can either use it, for example, as a pre-screen to select the most interesting models to go forward for a more detailed study within FEP, but can also be used in parallel to improve the prediction accuracy by combining the results from the two different methods. So let's wrap up by just looking at one application in the sort of context of a project data set here. This is again published in collaboration with Corteva. And this particular case was actually looking at finding a synthetic mimic of a macrocyclic natural product here. So this was the lead compound here, which is, as you can see, a macrocycle. It's a natural product. It's very complex, 4 chiral centers. Really, although very active, almost impossible to sort of get the sort of scale up with the cost of goods required, in this case for an agrochemical application. And so in the course of this project, it went from this macrocyclic compound to a fully synthetic lead series, which ultimately resulted in fluoropicoxamide, or FPX for short, which is fully synthetic, 2 fewer chiral centers, and non-macrocyclic. Now, in practice in this project, it took over 1,100 molecules to go from this starting point to the commercial product here. So we started with this set of just over 1,100 time-stamped compounds, so knowing the chronological order that was actually followed in the course of this project. And what we're going to look at here is an automated procedure of iterative refinement of a QuanSA model using an active learning approach. So this sort of is a very high-level illustration of the process. So the initial model was induced with 100 of the earliest molecules. All of these were from the macrocyclic series. So we built the model based on the earliest 100 with a good range of activities. So we build the QuanSA model. We can make affinity and pose predictions for all of the remaining just over 1,000 analogs. And then at each step, select the 10 compounds predicted to be most active, and also the 10 compounds predicted to be most informative with which to improve that model. We can then refine the model and make predictions for the remaining analogs that have not yet been selected. What was very remarkable is after only 3 iterations, the model began to predict the non-macrocyclic compounds within the top 10 most active predictions. And by only the 5th round, FPX was chosen as one of those active predicted molecules. So this is just 100 selected molecules versus over 1,100 in the actual course of the project. And this active learning strategy was critical to achieving this. So here you can see the alignment of FPX with the initial macrocyclic lead. You can see really good quality of prediction, and indeed you can see where it ranks here in terms of the overall correlation across these over 900 compounds. So in terms of QuanSA, they are physically motivated, physically realistic causal models of affinity. They can extrapolate from limited structure activity data. They can be purely ligand-based. They do not require protein structure. In fact, in that example with Corteva, there were no target structures at all available. And it can then be iteratively refined, as we illustrated, to improve the domain of applicability and prediction accuracy. QuanSA and FEP are roughly equivalent in accuracy and synergistic. And we just showed this one example here of how 100 well-chosen molecules were able to discover or identify the FPX product here versus well over 1,000 in the actual course of that project. Now, QuanSA is one part of our biopharmics platform, which provides a very comprehensive range of 3D ligand and structure-based design methods. And I guess one particular area, in light of the conversation we had with Dennis around macrocycles, is its ability to scale to handle very large macrocyclic compounds and provide both ligand and structure-based design approaches in these much more complex and flexible molecules. And I do need to acknowledge a lot of people. You'll have seen as I went by in little tiny writing at the bottom of the slides were the references, which are open access for all of the results that I've just presented today. So here, just a little bit more legibly in the top right are those references in case you want to sort of dig into all of the details and supplementary information. So thank you very much. In this particular case, literally taking the average. Nothing more sophisticated than that. You might be able to come up with something better, but that seems to work pretty well, actually. It is very simple. Question. Oh, yeah. Sorry. Yeah, absolutely. Great question. So obviously, yes, the question was, as the project progresses and you learn more and more about the binding conformations, the binding poses, can you actually feed that in? And what effect does it have in your ability to make predictions and sort of the synergies with FEP? So yes, I mean, if you start out in a project with no structural information, as I showed you, you can actually make really very credible predictions based on a binding hypothesis, based on a mutual alignment of known active compounds. But you can feed in that information. You can constrain that sort of that conformation and the alignment based on the sort of known poses of compounds, for example, in crystal structures. So you can actually do that. And yes, it will improve the accuracy of the model, or certainly you would expect it to. And hence, I guess, then you would see sort of greater synergies with FEP plus as well. That's a great question. I don't know. I don't know the answer to that. I guess it depends on how much you're biasing the predictions by the same structural input, and whether that is whether it is a bias or a more sort of representative of the true conformation. So yeah, I haven't actually looked at that. Yeah, so we can actually estimate the strain just using I think it's the MMF 94 force field. It's a very simple force field, but we can look at the strain relative to the global minimum found in a very rigorous conformational search. So you can look at basically include that energetic difference in the overall score of the molecule. It's not part of the machine learning, no. Yeah.